Hi, my name is Melina Songpan.
I'm Ethan Lee.
And I'm Joel Andrews, and the paper we will be presenting is titled Evaluation of the RC4 Algorithm for Data Encryption.
It was written by Alam Musa and Ahmad Hamad at Al-Najah University in Nablus, Palestine.
A quick review of this course. Encryption is the process of transforming plaintext into ciphertext. It runs through a formula that can be used to consistently produce the same result for encryption of the same data. Encryption and decryption use a key value to both encrypt and decrypt the data.
There are both private key encryption and public key encryption. Private key encryption uses symmetrical keys where both the sender and receiver have the same key and use it to encrypt and decrypt the data. Public key encryption is where two keys are used to encrypt and decrypt data.
There are two methods of producing ciphertext, stream ciphers and block ciphers. Stream ciphers are more simplistic in nature as each bit of data is encrypted using one bit of the key. The main advantage of this is speed and the obvious uses for streaming applications. Block ciphers encrypt data in chunks of a specific size, an example being DES.
The RC4 algorithm is a stream cipher symmetric key algorithm. It uses the same algorithm to both encrypt and decrypt the data. It uses a variable key length from 1 to 256 bits to initialize a 256-bit state table.
The state table is used for subsequent generation of pseudorandom bits, which generate a pseudorandom stream, which is then XORed with the plain text to give the ciphertext. During the initialization stage, 256-bit state table S is populated using the key K as a seed. When the table is set up, it is modified in a regular pattern as the data is encrypted.
First, we get the data to be encrypted and the selected key. We generate two arrays, initializing one array with the numbers from 0 to 255. The second array gets filled with the selected key. We randomize the first array depending on the key array, and randomize again within itself to generate the final key stream.
Finally, we XOR the final key stream with the data to be encrypted to give the ciphertext. Here we see a graphical representation of RC4. It should be noted that the key can be less than 256 bits.
A benefit of using RC4, as we said earlier, is that encryption and decryption is the same algorithm. On this slide, we have our encryption class object with its arrays K and S being the key array and the switch array respectively.
You will notice that we pass in the byte array's key into encrypt and fill K and S with I mod key, length, and integers.
Here we see the key at location I plus swap at location I plus the incrementer J all mod 256. This determines which integers in S get swapped.
Afterwards, we enter the portion of the code that builds our ciphertext, with another call to the swap function, followed by the XOR of some int K in our S array, with a bit in our plaintext cast to byte and placed into the ciphertext in order 0 to 255, after which we return our ciphertext array.
It should be noted that RC4 is no longer considered secure and is actually no longer supported on Microsoft Internet Explorer or Edge due to security concerns. Google stopped using it after the IETF put out a statement prohibiting its use.
All right. Now we'll move into our code demonstration. So here we'll just enter the standard hello world so that we can see our encryption. As you see, here's our encrypted string. Then if we press enter again, we get hello world. We want to do one more quickly. So we enter another random string, it could be anything. Here's our encrypted string, and then we just pass it into our decrypt class object, which just calls our encrypt again, and then it gives us back our original plaintext. All right, thank you very much.